Now, section 1.3, we're looking at partial fractions, and this is the idea. We know how to do this. We know how to start with two fractions and add them together and get this thing here. And we've practiced that in the previous section. It's a GCSE skill. What about going the other way around? What if I start with an algebraic fraction? On the bottom of the algebraic fraction are two factors. So I know that can have come from something over x minus 3 and something over x plus 1. So can I go the other way around? If I'm not given this bit and I'm given this, can I write that out as something over x minus 3, something over x plus 1, and is there a way of finding those somethings? Okay, that's the idea of partial fractioning. It's a useful algebraic idea, right? It turns up in all sorts of places. A lot of people, when they see it, think, well, what's this for? Why are we learning to do this? And there are two answers. One is, it's useful, but I can't tell you exactly why yet. You'll see some uses before we finish this blue textbook. And the other answer is, well, it's a thing that we can do with algebra. And what we do with algebra is we just try and find as many different techniques and ways of looking at things as we can. And that's just what we do. We play with algebra as mathematicians, right? So let's have a look at how we actually do this then. So this is our first step. 6x minus 2 over x minus 3x plus 1 must have come from something that looks like this. It must have come from something over x minus 3 and something over x plus 1. Now, you might think, well, okay, how do I know it's a constant here and a constant here? How is it not ax? You know, why is there not an x term on the top or an x squared term on the top? Well, if you imagine adding these fractions together, you're going to do this thing times by x plus 1 and this thing times by x minus 3 when you make your common denominator, aren't you? Well, if you do that, then you're going to get a linear term here and a linear term here to add up to a linear term. If I put an x in here, so let's have, let's make this a linear term on top. So something x plus something over x minus 3. Well, when I go to add these fractions together, I'd have to times the bottom here by x plus 1 and times the top here by x plus 1. And then what have I got on the top here? Well, I've got an x term times an x term. I'd have a quadratic term on the top here. And same if I made this, instead of a constant, if I made this into a linear term, I'd have a quadratic term here, and then I'd have quadratics. Now the numerator on this side wants to be the numerator here, so I can't have a quadratic making a linear term. So that's why I have constants. Now don't panic about that. If that doesn't make sense, maybe rewind it and watch it again, but really, trust me, these are just going to be constants. Okay, let's get the main tactic of partial fractions under our belt first, and you can always go back later and see the details as to why that works. Okay, so this is how it works. 6x minus 2 over x minus 3x plus 1 equals this. Now this isn't just an equal sign, this is an identity sign. This is something of, equivalent to 4x equals 2x plus 2x. This is a rearrangement of an algebraic expression. It's not just an equation that works for some values of x. 2x plus 2x is always equal to 4x. These two fractions added together are always going to be equal to this fraction. So it works for all values of x, and that's important because we're going to do the following. We're going to say, well, let's times by this common denominator. And what do we get? 6x minus 2. If I times by this denominator for this fraction, I'm going to get a times x plus 1. Because, just to spell it out, you might want to fast forward this bit if it's obvious to you. But if it's not, don't worry. If I take that fraction and times by that, that's what I'd get. They would cancel out, and I'm going to end up with a times x plus 1 left. Okay. In the same way, I'm going to get b times x minus 3. Okay, so I'm going to end up with this statement, and again, it's always true. Now, from here, there are two ways forward, and I'll show you the way that I like the most first. A times x plus a plus b times x, b times minus 3. So this right-hand side is equal to a plus b, lots of x, and a minus 3b is my constant bit. Okay. Now, if this linear expression here has to be the same as this linear expression here, then what I'm saying is that 6 has to be equal to a plus b. Why? because I've got 6 x's here. How many x's have I got over here? I must have 6 x's. Now that is called equating coefficients. And the way we often set it out is that this is the x to the power of 1 coefficient. And then I'm going to do the constant term as well, so that's the x to the power of 0 coefficient. So you can imagine if I had an x squared term and an x term and a constant term, I would be equating the coefficients of the x squared term, equating the coefficients of the constant, and equating the coefficients of the x squared, equating the coefficients of the x, equating the coefficients of the constant. So I do it in powers of x. So 6 has got to equal a plus b. Well, fair enough. But then minus 2 has got to equal this thing here, a minus 3b. What have I just got? I've got two simultaneous equations in a and b. So I can solve those two simultaneous equations, and if I do that, well, let's write this one as a equals 6 minus b, and substitute, so I'll call that 1, we'll call that 2, sub 1 into 2, we're going to get minus 2 equals 6 minus b minus 3b, minus 2 equals 6, minus 4b, take away 6 on both sides, minus 8 equals minus 4b, so b is equal to 2, and from this equation here I can tell us that a is going to equal 4, and with any luck I've got the same answer as the book I have, so a equals 4, okay? So I get, in this expression way up here, a is 4 and b is 2, so you'll have to write it out, but I'm just going to do this. There we go. And that was what we started with, wasn't it? We said I started with telling you that was true. Well, that's how we found the 4 and the 2. So that's tactic number 1. Now, here is tactic number 2, and unfortunately you need to know both of these. So this is the equating coefficients method. That's the one I like the most. I think most people disagree with me, if I'm honest. I think most people prefer this method, which goes like this. First of all, you do the same thing up to here. Now what we do is you say, well, if 6x minus 2 is exactly the same as a plus b, we do the same thing up to here. 6x minus 2 is the same as a times x plus 1 plus b times x minus 3. Well, those things are identically equal. So let's have some clever thinking. Let's say, well, what happens if x equals minus 1? Well, on this side, I get minus 6 minus 2, so I get minus 8. On this side, I get minus 1 plus 1 is 0. So that term vanishes out. I get b times minus 4. So minus 8 equals minus 4b. So b equals 2. Well, if that's all right, I've got a b, so that's lovely. So I can go back here and change it into a 2. If you're in an exam, of course, you'd have to write this out again with the 2 in there. What happens if x equals 3? Well, in that case, I get 6 times 3, which I think is 18, take away 2, so 16 equals a times 4, plus b times, 3 take away 3 is, wasn't it clever that I chose a 3? This turns out to be a 0, and that all vanishes, so 16 equals 4a, so a equals 4. There's my b, there's my a, okay? And that is the substitution method. Now with substitution, just watch out. A lot of people think, well, I've got to pick the value that makes this bracket equal 0 and pick another value that makes this bracket equal 0. That's not true. You can pick any values you want. So I could put a equal to 0 and I'd get minus 2 equals a minus 3b. I could put a equal to, let's take a silly example, a equal to 7, so I get 40 equals 8a plus 4b. Now, what I've got there is two equations which have got a's and b's in them. I can solve them simultaneously. So if you do all the clever values and you still need more equations, just pick any value you want. Sorry, not a equals 0. X equals 0, x equals 7. So if I pick different values for x, then I can get equations, all right? It doesn't have to be clever values. But obviously, if you pick a clever value, if you put x equals minus 1 in there and this one vanishes, then you're going to get a nice simple equation like b equals 2, instead of a nasty, horrible, complicated equation like 40 equals 8a plus 4b. All right? So that's the substitution and the equating coefficients method. And that's really the important one for the whole of this chapter. Everything else we do relies on us being able to do those things, okay? One more thing that I will mention, because if you're working through the same textbook, it's the last thing on section 1.3. If you started with something which has got 3 factors on the bottom, then you need to write out each of the factors. Oops, x minus 2, x plus 6, x plus 3. So you've got 3 fractions to work with here, a, b and c, and from there the method works the same. If you're working through this textbook, it's page 10, example 9, and you can see it in the blue box from there. But that gives us everything on exercise 1D. There are more things with partial fractions, but I strongly recommend that before you look at the next section of this, you practice those basic techniques. Now, they might not seem that basic, they might seem a bit fiddly, but when you've done them a few times, you'll see it's the same every time. And once we've learned to do it, we can just tweak it a little bit for slightly harder examples. But really, if you can do that, you can do the hardest bits of partial fractioning that you're going to need to be able to do. Okay, that's the end of that section.